Now you will see that in many a case we have an inclined plane and the bodies are moving on that inclined plane. The inclined plane itself may be movable. In this particular case it is not, it is fixed. So what happens in such cases and how do we go about the question in such cases? We'll discuss that by taking one of the most simple example. Like in this case, a mass is overhanging. It's similar to the case earlier where you had a body like that and mass was hanging. Here we said that this mass is no matter how much ever big, the body has to move that way. Here it is not the case. We can feel that if this mass is very large, it will go this way. If this mass is not that large, it will go that way. So let me ask you one simple question before we proceed. If m is equal to capital M in this case, which way is the mass going to go? I guess you have guessed it right. Let me put a value and put another question now. If m is equal to say 5 kgs and capital M is say 8 kgs and this angle was say theta was equal to 30 degrees, which way will it go? What do you feel, which way will it go? Theta I have taken 30 degrees, but I am insisting you not to do any calculation, and you can say, can't say unless precise calculation is done, or you are sure that 8 is more than 5, hence it is going to go down. What's your logic over here? So just think of that and pause the video and think over it and then come back. So now suppose it is 8 kgs and this is 5 kgs. Now why will this go down if this was lesser kg? Why will it go down? It goes down because the earth pulls it down. Earth pulls it down with 5 into g, means around 50 newtons force. It is going to pull it down. Now why should this side go down? Because the earth is going to pull it this way. And earth is going to pull it down, but it will have an effect this way, and that effect, if it exceeds the pull this side, if the earth's pull which is downwards, whose effect is forward also, if that effect counters this pull, then only it is going to go down. So the 8 kg mass has a total weight of 80 newtons, that is mg, capital mg downwards, but then that mass is not pulling this guy up. This weight is not pulling that guy up. Here also this mass may have been a very large mass with a very big weight, but that had nothing to do with the pull on this body. So this time, since it is on an inclined plane, it has got something to do, but not the whole of it. So it is only a part which is pulling it. So what we are going to do is, we are going to resolve the weight in two directions. One direction where the action is happening along the inclined plane, and since we have made a component in that direction, we need to have a component in the 90-degree direction which is having no effect in the direction of the inclined plane. So what will be these two components of mg? Let us study that first before we get to know this answer. So for now, I don't know whether it is going to go this way or that way. 8 is greater than 5 doesn't justify this going down, because the whole 8 kg force weight is not acting this way. A part of the weight is acting. So I'm going to figure out how much is that part. So no friction and all. So let us figure out the angles in this. And once we have figured it out, just remember it for a long time. So this angle is theta. We can consider this as a 90-degree triangle. So this dot angle, I'll draw in red. The dot will be 90 minus theta. Now this total is 90 degree. So this angle again would be theta. So what we get over here is, and remember this for a long time. So I'm going to draw it over here in star. What is that? If you have an inclined plane at theta angle, then if you are considering a normal to the inclined plane and vertical to the horizontal, so the angle between the inclined plane and the horizontal is same as the angle between the vertical and the normal. This is the vertical, this is the normal. So this angle is equal to that angle. So that is what we have derived over there. I can just derive it again over here. This is theta, this is 90 degree, this is 90 minus theta, hence this is theta. The angle between the vertical and the normal is theta. So that you don't forget it, I'm going to demonstrate this again for you because I want you to remember it for a long time. If this is the horizontal, that's a horizontal line, and that's an inclined plane, and that's the normal to the inclined plane. So if the inclined plane is along the horizontal line, and I'll draw a vertical somewhere. So this is the inclined plane, and this is the normal to the inclined plane. This blue marker is the normal to the inclined plane. So if I make the inclined plane go like this, the normal to the inclined plane will also turn accordingly. So look over here. If my inclined plane was absolutely flat, then my normal is absolutely vertical. Now if my inclined plane goes up by angle theta, then the normal leaves the vertical by the same angle theta. You can see that. It is going up by theta, it leaves the angle by theta. So here, if it has gone by say 45 degrees, then it has left by 45 degrees. 50 degrees, 60 degrees, then it has left by 60 degrees. So the angle what the incline is making with the horizontal, that's this angle, the incline, whatever the angle the incline is making with the horizontal, the normal to the incline is making that angle with the vertical. So initially incline is making 0 angle with the horizontal, normal is the normal is with the vertical. So that is how it leaves. So what am I doing over here? I am giving you a physical sense of a very simple mathematical situation. So in physics, I would like you to study everything in terms of with the eyes of a physicist and not a mathematician. So here what I've proven through geometry, I'm just showing you a sense of how it is. So that was your mg, which was vertical. So if I cancel out mg and draw the two components, then the two components, one along theta, would be mg cos theta, and away from the theta, this is 90 minus theta, so that is mg cos of 90 minus theta, which is mg sin theta. So your weight, which was mg vertically down, is not taken as mg now, and in most of the inclined plane situations, we'll be taking the weight as two weights in two different directions. One is mg sin theta along the incline, and one is mg cos theta normal to the inclined plane. Mind you, these two vectorly added, which is mg sin theta whole square plus mg cos theta whole square under root, is going to give you back mg. So these two are effectively mg only, but the one along the inclined plane, the effect is mg sin theta, and one along the normal, the effect is mg cos theta. So here, to know whether this guy will get pulled up or this guy will get pulled up, we have to see how much they are pulling each other. This big mass is pulling the string by mg sin theta, and this guy is trying to pull it by mg. It is, the tension will not be mg or mg sin theta if they move. If they are not moving, if they were not moving, both were stationary, then that is the maximum pull what they can give to the string. So who wins? So in this particular case, if I do a sin mg sin theta 8 times g and sin theta, sin 30 is half. So you'll get a 4g force over here, and this is 5g. So this will be a 4g force, that will be a 5g force. So even though this is massive, it is 8 kgs, it is going to go up because the incline made the effect very less. Had the incline been steeper, had it been at say 45 degrees, then your sin theta would have been a greater value. Bigger the angle, bigger is the sin theta value, and bigger this component becomes. At 90 degrees, you can imagine sin 90 is 1. So it will be the whole mg will be acting. So as the incline goes down, it is lesser effect, sin theta goes down. When theta is 0, sin theta is 0 and has no pulling effect. So no effect of gravity along the string in this case. So what's the situation over here? Let me just quickly make the equation for both ends. You can consider the whole thing as 1, and since the body is going with AA acceleration, this with A down and this with A that side, I can quickly write down that the acceleration A will be equal to the net force. What is the net force? That is mg from this end is pulling down and this end is pulling this way with mg sine theta. So that's the net force divided by the total mass. How much mass is being pulled? Both masses, m plus m. I guess we are going to get this answer, but we are going to do in the preferred way. What is the preferred way? Writing horizontal and vertical equation for this mass and writing two equations for this mass along the incline and 90 degree to the incline. So here horizontal has no forces, so we will not write an equation, and along the vertical it is going down. This force was mg and tension upwards. So this is the contact force. At times I see that you are applying some tension somewhere else on the body. What is touching the body is pulling the body. So what is over here? mg minus t is equal to, that's the net force on the body downwards, and the acceleration is also downwards, is equal to mass times the acceleration. That's your equation number 1. For this body we can write two equations, and what would those equations be? One along the incline. So along the incline acceleration is known, that is a. So what is, how much is that? That is, t is the pull. So we have t minus mg sine theta is equal to, t minus mg sine theta is equal to mass of the body into acceleration. This acceleration and this acceleration are the same accelerations, hence we are writing a, otherwise we would have not. So here we have seen the constraint a, and a is the, both accelerations are same. The constraint is 1:1. Now equation in this is also there, maybe not required. Why? Because we have two unknowns, t and a, and we have two equations, so we are done with the thing. But just to ready ourselves for future questions, let us write the equation in the vertical direction, in the 90 degree to the inclined plane direction also. So what's that equation? This mass is pushing the block with mg cos theta. Why is it not going in? It's not going in because it is experiencing a push. Since it is pushing, it is experiencing a equal and opposite push from the wedge, and that is called your normal reaction. So the normal reaction on the wedge I am not drawing because wedge is fixed to the ground, so no use of making forces on that. I am pushing the wall, no use of pushing it, it is fixed. So what is the equation in this direction? Equation in this direction is mass into acceleration in this direction is 0. So net upward force must be net downward force. So in a simpler way I can write n is equal to mg cos theta. Now here again, in say 60-70% of the questions you are getting n is equal to mg cos theta. So don't memorize that normal reaction is mg cos theta. Normal reaction at times in such situations is mg cos theta, but where the wedge itself will be moving and all, normal reaction will not be mg cos theta. Same as when we have a platform, on the platform there is a mass. If the platform is not moving, this is the green platform which is not moving, then your normal reaction is equal to mg, because the mass is not moving, because since the platform is not moving, mass is not moving. But if the platform is going up or if the platform is going down, then n is not equal to mg. Similarly over here, n will not be equal to mg cos theta in all cases, particularly the cases where the platform, which is the wedge itself, is moving. So that's the equation number 3, which is not going to be used in this case because there is no friction and all. So the normal reaction is going to affect the friction in that direction, which is going to come later. So taking equation number 1 and 2 and solving, plus you can see that equation number 3 has introduced a new variable. So with two equations we have two variables t and a, with three equations we have three variables t, a and n. So extra equation with the extra variable in it. So no use as such of the equation. This is an independent equation, mg cos theta. Theta is known, g is known, m is known, n you will get from there. So adding the two, 1 and 2, what do we get? 1 plus 2, equation 1 plus 2, t gets cancelled, we get mg minus mg sine theta is equal to, this side gets added, m plus m A. So that's the equation. Here all the variables are gone, only A remains. So we can find out A by putting that down. And what we get? We get this. So we had avoided writing this and just using our earlier concept, we had written that equation, but I'm not advocating that to you much. I'm asking you, I'm pleading you to write these so that you understand the situation better and know the tension forces. And simultaneously, I also want you to know that this can be done. That I'm not going to repeat all of this with application of this concept. Hence, I'm writing that, but I'm not suggesting you to go this way. Okay, so what we have over here, we have that along the inclined plane, the weight of a body would be mg sine theta if m is the mass, and 90 degree to the plane, the weight will be mg cos theta. The angle between vertical and normal is the same as the angle between horizontal and incline.